Hello, good day, Doc H. This is our group consisting of myself, Tristan de Guzman, Sean She, and Tomas Santos, and we are going to be presenting our project, the Emergency Lighting System. So, to introduce our project, we all know that power outages have been a common and long-standing problem in the Philippines. This can cause safety risks, especially during the period wherein uh, you don't have any lights, you don't have any electricity, and you're fumbling for a light or fumbling for a flashlight or a lamp, right? And this need for reliable emergency lighting is something that we want to address, which is in line with SDG 11, that being the aim to make cities and human settlements inclusive, safe, and resilient. Now, this is a shift from our original design, the water tester, since we decided that it would be too costly to effectively implement in communities in the Philippines. So we moved to the emergency lighting circuit. So the initial design was included a transformer, a rectifier, a 9-volt battery, and a couple transistors. And this original design will be found to be complicated, number one, which would hinder like the use, which would hinder those in outlying communities to be able to effectively implement them. And number two, it would be costlier or more costly than the second revision of this circuit. So the final design, we simplified the circuit. We made it more reliable since in our testing, the initial circuit at times was not responsive. So now we have a 110 volt to 6 volt transformer, step down transformer. We have a few diodes, two to be exact. We have one BD 140 transistor, uh, a 2.4 volt battery, and two LEDs. And so our circuit auto activates during outages, and it is a low cost and effective solution to the problem that was mentioned a while ago. Next would be the materials. These are the materials, and as you can see, the price totals to 420 pesos, which was a far cry from the original price of our first design, which was 750 pesos per per circuit.
So for methodology, so for starters, our circuit design starts with a transformer of 110 volts to that is step down transformer to 6 volts, and it's connected to two diodes that can serve as like a full wave rectification to smoothen out the AC voltage to DC. And it goes through a 470 UF capacitor for smoothing out the output signal, which is around 7.8 volts DC, which is the output signal. And after that, it'll be leaded to a PNP transistor, or what we call as a BJT, with a model of BD140 as like a switch to interchange between two power sources. One is the transformer and one is the battery source. So for our battery source, we chose a 2.47 volts battery source, and we connected to two LEDs with 300 ohms resistor that is pulled down to ground for a stable control. So the total operation will be like when the transistor is off or when it's plugged off, it when the transistor is off, the LED will be off, so no battery will be used, which means it's plugged in. But when the power outage, when it will cause the transistor to be on, and the LEDs or the emergency light will then light up instantly. And next, for the next part, which is the improvements of this design, is of this newest design, is that it reduces more components, more simpler circuits, so people can use it more and design it more easily. It changed from 9 volts to 6 volts, which is a less of what required of voltage, and from a lot of bridge diodes to two diodes, dual transistor to only one single BJT, and we removed the charging circuit. Instead, we use just a battery, fewer LEDs, and it's more simplified. In terms of testing, when we're testing, in normal state, LEDs will be off, battery will be not draining. But when it's brown out, LEDs will be turned on, and there will be a current going through. And it's verified. The voltages and the battery performance are also verified. So as you can see in our circuit, it starts right here. Right here, it starts in the 110 volts to 6 volts transformer, connects to the diode, which is also connected to a parallel of a capacitor parallel with a 300 ohms resistor. That is also connected to another diode, and which is connected to the emitter of the BJT. And the base is then connected to the two LEDs, while the common ground is connected to two resistors along, along with the feedback to the diode to the emitter, and they're all over parallel connected to a battery source.
So for the results and discussion, we have the performance results where we have the 7.4 volts DC with the AC from the transformer, which lead to the BJT turning off and the LEDs to turn off. And the power loss, uh, when the power is cut off, rather, the LEDs turn on in less than 5 milliseconds, so almost instantly. We have a 12 milliamp current draw with a steady brightness, and the battery runtime is above 4 hours from what we have observed. Now, to compare to the original design that we had, the original was rechargeable, had three LEDs, and was a complex circuit, but it had many issues, like the charging itself caused issues, instability due to the more complex circuit, and component availability. So the final one is simpler, more stable, and easier to build. Next, for the significance, of course, it's important to have lighting, especially during brownouts and outages. There is a low cost for the overall circuit, less than 450 pesos, and has accessible parts. And it supports SDG 11 for safer cities since it helps individual households be more safe during blackouts or individual spaces to be safe. And it is a good educational demo of basic electronics. Now, to the improvements from the original design, we have a single transistor which leads to less noise and errors. We have a lower voltage, around 2.4 volts, which helps for more batteries, for more kinds of batteries. And we have fewer components and a safer design. For the conclusion, overall, we shifted from the complex rechargeable design to a simple PNP design. The final circuit is functional still, reliable, and lower cost. We have an instant detection of power loss, so the LEDs turn on immediately, which would be important during emergencies. And although we did remove the charging feature, we kept the core functionality and the most important part, which is that it works during power cutoffs and it is fast. So we demonstrated automatic emergency lighting principles, and it is a very practical, accessible solution for power outages. In the future, we could add charging and make a more robust design. However, this simplified design still meets objectives and improves safety.
Hi, I'm Tomas Santos, and this is my list of contributions for the Circuits 2 final project. Which was the emergency lighting system with my group mates Sean, She, and Tristan de Guzman. So for my contributions, I helped with the first and second design, along with the calculations for these circuits to see if it would actually work. And of course, I actually also helped assemble them in the labs with my group mates. And I worked on the Google Docs, the documentation for it, along with the presentation. And yeah, my group mates and I all did the same tasks and we collaborated on pretty much everything. So yeah, thank you.